Welcome to our presentation on significant figures and orders of magnitude in relation to measurements. Let's begin by exploring the rules for determining the number of significant figures. Accuracy is important when working with scientific data, and significant figures represent the level of accuracy of a measurement. Being conscious of the decimal points in a measurement is key to avoiding mistakes. Rounding off measurements when necessary is a must to ensure accuracy and effectively convey the data. We will examine significant figures, which represent the figures seen to be dependable when determining a numerical value. As an example, when measuring pi, it may be observed to have 10 digits, in other words 3.141592654. This can be truncated to 3.14, with 3 digits, or 3.1416, with 5 digits. The amount of significant figures presents the veracity of the measurement. When determining the number of significant figures in a given number, all the non-zero digits are significant. This includes any zeros that occur between two non-zero digits. For example, 18,452 has 5 significant digits, and 1,845.2 and 184.52 also have 5 significant digits. When dealing with numbers, knowing how many of the digits are significant is essential. In the case of 106.008, all digits have importance as none of them are zeros at the end of the number. But if the number is smaller than 1, such as 0.000308, the zeros before the first non-zero digit are not considered significant, so in the example, only the 3 is relevant. This is something to keep in mind when working with numbers. Understanding units and measurements of a number is essential. As an example, 30.00 has 4 significant digits, all the zeros to the right of the decimal point having value. On the other hand, zeros to the right of the last non-zero digit in a number without a decimal point are not significant. For instance, 2030 has 3 significant digits. Having a proper understanding of each term and definition can help greatly in calculating and using measurements. Reliability of digits in a measured quantity is determined by the number of significant figures it has. If the quantity has insignificant figures, then the reliable digits in it are in 1. This knowledge is essential when interpreting and analyzing data. A classification method for the measure of a physical value is known as order of magnitude. Usually this is done by using a power of 10. When looking at the numbers, the exponent of the power of 10 stays the same. As an example, if going from a value of 0.1 to 1.0, or 1 to 10, there is a change in the order of magnitude. To put it simply, it is a method of expressing large numerical values in terms of the powers of 10 which they are based on. The order of magnitude of 1.23 times 10 to the 2 kilograms is 10 kilograms, and the order of magnitude of 6.527 times 10 to the 3 kilometers is 10 to the power of 4 km. To calculate the order of magnitude, identify the number before the decimal point for each value. If the number is less than 5, the order of magnitude is 10. If the number is 5 or greater than 5, the order of magnitude is 10 plus the number before the decimal point. A day has an order of magnitude of 10 to the power of 5 seconds. It is equivalent to 8.6400 times 10 to the power of 4 seconds, or 86,400 seconds, when divided into 24 hours. The mass of a proton is 1.67 x 10 to 27 kilograms. Rounded to the nearest power of 10, it is 10 to 27 kilograms, an incredibly small amount. This highlights how important it is to be accurate when working with measurements and units. Non-zero digits are significant figures. For instance, 16 has two significant figures, 1683 has 4, and 16,835 has 5. Also, any zeros between non-zero digits are counted as significant figures. For example, 802 has 3 significant figures, and 80,004 has 5. The important concept of unit and measurements is illustrated in this slide. As can be seen, 0.40 has 2 significant figures, while 0.030 has only 2 significant figures. Power of 10 are not considered as significant digits. For example, 1.4 x 10 to 2 has only 2 significant figures, 1 and 4. All zeros to the right of a decimal point and to the right of a non-zero digit are significant. All numbers, be it whole or decimal, have a certain number of significant figures or digits. The number of significant figures is determined by counting how many digits are present to the right of the last non-zero digit. For instance, the number 40 has only one significant figure as the last non-zero digit is 4. On the other hand, the number 410 has 2 significant figures, and the number 40,240 has 4 significant figures. Though, all zeros to the left of a non-zero digit are not considered as significant figures. For instance, the number 0.08 has one significant figure, the number 0.008 has one significant figure, and the number 0.0806 has 3 significant figures. Examine the number of significant figures in a set of numbers. Start by counting the digits beginning with the first non-zero digit and ending with the last digit. For example, 0.05718 has 5 significant figures, 93.26 has 4, and 2.35 has 3. When multiplying or dividing, the product or quotient can have up to the smallest number of significant figures of any of the components. For instance, multiplying 0.05718 and 93.26 results in 5.33, which has 3 significant figures, the same as 2.35. The answer to this multiple choice question is B, 3 inches. This is due to the fact that 0.0009 has 3 significant figures, since the trailing zeros are not taken into account when determining the value of the number. Answer. Option B, 2 is the correct answer for this question. Significant figures in measurements include all digits except the zeros that begin or end the number. Thus, 0.400 has 2 significant figures, 4 and 0. Accuracy of a measuring instrument plays an important role in determining the amount of significant figures. Generally, higher accuracy of the instrument leads to a more accurate number of significant figures obtained from the readings. Rounding numbers refers to the process of changing large decimals or fractions into a simpler form. This is done by taking the number to the nearest whole number or decimal. Having the ability to round off numbers is essential when making estimations or when dealing with long calculations, and is a necessary skill for any mathematician. Omit all non-significant digits and retain the desired number of significant digits, then apply the rules of rounding off. If the immediate insignificant digit is more than 5, the preceding significant digit should be increased by 1. For instance, 4,728 rounded off to 3 significant figures would become 4,730. When dealing with units and measurements, precision is essential. In the mentioned example, if the digit to be dropped is less than 5, it should be rounded off to the nearest 3 significant figures. For example, 4,723 would become 4,720. However, if the digit to be dropped is 5, then there will be two different cases. When it comes to units and measurements, rounding off is an important factor to take into consideration. For instance, 4.7253 should be rounded off to 2 decimal places. This means that the 5 and the 3 preceding it must be dropped. In this case, the preceding digit, 2, is even, so it needs to be retained, leading to 4.7253 being rounded off to 4.72. Therefore, when the preceding digit is even, it should remain the same and the 5 should be dropped. Identify the preceding digit in the number, and if the preceding digit is an odd number, add 1 to it. For instance, 4.7153 would have 1 as the preceding digit, an odd number, so when rounded off to 2 decimal places, it would be 4.72. It is important to remember that when multiplying or dividing numbers with significant figures, the result should retain the same number of significant figures as the original number with the least significant figures. This will help keep the outcome as precise as possible. We'll look at units and measurements. As an example, adding 2.2, 4.08, 3.12, and 6.38 gives a sum of 15.78, which should be rounded off to 15.8, due to only needing 1 decimal place in the final answer. Multiplying 1.2, 2.54 and 3.26 together produces a result to be limited to 2 digits, equaling 9.9. As you can see, this slide is asking us about unit and measurements. The goal is to round off 4.9283 to 3 significant figures. The answer is 4.93, and if the digit to be dropped is greater than 5, then the preceding digit is to be increased by 1. Working with units and measurements can be complex, but this slide illustrates one way to approach the problem. With that, thank you for your attention.